Hello everyone, I'm Akarken. For this summer, I was working on high-performance system analytics project in Surf, Netherlands. The main source of the project is the previously published paper, A Holistic Analysis of Data Center Operations. On paper, it is demonstrated that the benefits of holistic analysis method by applying it to the operations of a data center infrastructure with over 300 nodes. Also, it is suggested that such observations can help immediately with performance engineering tasks such as predicting future data center load and also long-term with the design of data center infrastructure. And therefore it is proposed to analyze operational logs with machine learning methods. Starting from the previous work, where operational logs of the cluster computer these are characterized, the project proposed a continuation that would bring in scope additional data sources like Prometheus. It's planned to evaluate an anomaly detection method on this newly created dataset. Among the sources that can be selected as data sources are EAR, HALT, Slurm, and Prometheus. We continued the project with Prometheus data. Prometheus is an open-source system monitoring and alerting toolkit that provides information in the form of operational logs at the node level. In this project, we aim to produce a new dataset using Prometheus data and to detect anomaly using machine learning methods. First of all, we analyzed the data we obtained with Prometheus and applied some processing method and made it suitable for giving as input to a machine learning model. Afterwards, we found and cleaned some outliers in this data and thus made the dataset suitable for model training. And then we made experiments hyperparametric tuning by choosing a suitable model. First of all, I would like to talk about the data we have and what kind of pre-processing we do. The dataset we use to train the model consists of 280 CPU nodes. Thanks to Prometheus, a new data point is produced every 30 seconds, and we can reach this data point by an API which consists of approximately 80 features. Although uniformity is tried to be ensured at the node level, the data points are not uniform in themselves. In our project, we use 6 days of logs of these 280 CPU nodes. For example, different nodes may use different file system files. This is one of the biggest obstacles to normalizing data. Here, we normalize the data at the feature level using different aggregation techniques. In the studies conducted with the machine learning method, the power usage feature was primarily used as it would be easier because it follows a certain trend. Power usage represents the CPU usage in the node. For example, if the CPU usage is high on a node, it will likely be high at the next data point. We decided how much of this normalized data we would use by using PCA. As a result of the PCA analysis we made with different component numbers, we realized that we could cover 97.9% of the information about the data by using 15 components, and we used 15 components in our next analysis. The features providing maximum variance in the data by PCA analysis are node disk written bytes, node course temperature, and the features related to node network. Afterward, we took another step to create a new dataset by detecting the outliers with PCA. We calculated the error rate by using the principal components and their inverse transform with the mean square error method, and we realized that 95% of the data has an error rate in the range of 0 to 5. While the remaining 5% was accepted as outliers and eliminated, we continued our work with this 95% portion. What we see here is the 3D view of our PCA analysis. Frankly, we expected to observe some clusters at first, but the analysis gave us a linearity result, and we got this result even though we didn't use timestamps as inputs. We choose LSTM, which is a machine learning method where we can use a new dataset we obtained. LSTMs are the preferred method for time series data as they can use long-term observations. That's why we started using LSTM. In LSTM, we first estimated the CPU usage as I explained the reasons earlier. We decided that we could do an anomaly detection with a model that could make accurate predictions for CPU usage for the next step. We started our first work with LSTM using information about the single node. Since LSTMs are powerful models, they started to overfit on such a small dataset. We also played with different parameters to overcome this overfitting. These parameters include dataset size, batch size, input sequence length, number of epochs, hidden layer size, and output size. These are the results for our experiment with changing hidden layer size and sequence length. As a final model, we used a model with a hidden layer size of 16, input length of 64, and a batch size of 512. In order to avoid overfitting, we had increased our dataset size fivefold, and instead of using all features, we have started using 45 features, which corresponds to 64% of all features. Based on our assessments, LSTM is promising to be good at predicting, especially in areas where data spikes, but as always, there is room for improvement. The next step is to create clusters for normal data points by clustering the outputs on the dense layer of LSTM and to consider the data points other than this as outliers. In addition, some questions come to mind. For example, can we get better results if we use the components we obtained as a result of PCA analysis as LSTM input? Or what does the linearity we see as a result of PCA analysis represent and goes? These are some of the questions that will be answered as a work progress. Thanks for listening. I'm waiting for your questions.